Today the presentation will be about how does EDA benefit from the AI revolution. So now let's first look at what is AI. So here I have a picture from Hans Moravec, and so you can just imagine there's an island, and there are mountains on the islands, and there are peaks. And each peak stands for a certain human capability. So one capability is playing chess, then write a poem or prove a theorem. And now there's a sea around this island, and the sea stands for artificial intelligence. And the sea level is rising. And then at some point, the sea level covers a certain peak. So that means that AI has overtaken a human in this specific capability. And with the time, as the sea level is rising more and more peaks get covered. And so so this is the prediction. At some point, the whole island will be underwater. And then this is the point where we have reached the general AI. So question is, so how clever is AI? And so a very naive approach would be, so AI is artificial intelligence, and to measure intelligence, we have the IQ tests. Yeah, so there were a research by some Chinese students, and they measured the IQ of some AI systems. And they did it in 2014. And so you see that the average AI of a 6-year-old human is around 55.5. And at that time, so the Google Assistant reached a score of 26.5. So it still was very premature. In 2016, already Google caught up, and so was already at 47.2, so which is kind of comparable with a 6-year-old human. So now in 2022, ChatGPT was released, and somebody on the internet just made such an IQ test, and suddenly ChatGPT scored 83. So which is already beyond a 6-year-old child, and even beyond a 18-year-old person. So of course, so here people in the room, so who are familiar with AI, so we will say, well, so this is not a fair comparison, so that machine intelligence and human intelligence are different. So IQ tests cannot be applied to machine intelligence, but just the discussion. So what is machine intelligence? So what are machines capable to do, and what are humans capable to do? So compare this kind of intelligence. So it's already a technical, but also a philosophical question. So now let's talk about the revolution. So where does the revolution come from? So revolution is usually something when old assumptions are no longer valid. And so far, AI was not considered as something dangerous, or something that will take the workplaces away. And the paradox is that if we reach a certain stadium for a certain system, so then we don't consider them as intelligent anymore. So let's imagine in the 80s, if somebody would tell that there will be a machine which can play chess better than a world champion, which can navigate through the streets, which can recognize speech. So then the person from the 80s would say, well, this is something very intelligent. So now we have chess computers, we have Google Maps, we have Amazon Alexa, and now everyone is using this and say, well, it's not intelligent at all. So we understand how it works. So we understand there are some clever algorithms, but it's not intelligence. So with the release of ChatGPT, so then suddenly there are some reports that there are some experiences where researchers who are talking to this kind of systems, they seems to find a glimpse of intelligence here. So therefore, so this is, I think, quite a major milestone achieved. And in November 30, 2022, ChatGPT was released. January 23, already over 100 million users. And then, so November, January, they were following assumptions. So that ChatGPT and other systems, they can be created only by very few major companies, and they have to invest millions of dollars. They have to have a very expensive and exclusive hardware. So this is something which can be regulated. And you might also remember there was a letter posted by some of leading companies on AI, and they said we want to have a 6 months moratorium on AI research. So we want first to evaluate how it can become dangerous, and so we want to stop the research. So what happened just 1 month later? So an open source GPT model was launched. It was accessible to academia only, but then 2 weeks later, so it leaked to public. And again, 2 weeks later, it was proven that it can run on a Raspberry Pi. So of course not in acceptable speed, but it's possible. So it means that you don't have you don't need expensive hardware. You don't need so you can run it locally. So then just 2 weeks later, thanks to a quantization of the model, so this Llama can run fast on a MacBook CPU. And then another 2 weeks later, so Vicuna was released, which reaches the parity with one of the big LLMs, and the training of this was around $300. So basically, that means that the technology is no longer exclusive to big companies. So basically, everyone can just download a model on private computer, do additional training on it, and so basically the genie is out of the bottle. So the technology is no longer it can not longer be controlled. And so this, I would say, it's a revolution. And so this list stops on April 3rd, but I'm sure that in the meantime, even more developments and breakthroughs were done. So how is this all related to EDA? So if you have attended an industrial conference recently, so you've probably seen a variation of this slide. So we are talking about 1 trillion revenue in the semiconductor business by 2030. And since semiconductor is a foundation for the electronic systems, so here the electronic system market is also profiting. So here we are talking about 3 trillion, and the major growth comes from areas like 5G, hyperscale computing, autonomous vehicles, AI, and industrial IoT. So this is something that these numbers are already widely known in the industry. But these numbers are something that Cadence did an analysis, and so the claim is that the complexity of the designs will increase by factor 100 over the next decade. So where does the complexity increase come from? So first, we are moving to lower nodes, so which is a complex stuff on itself, but also there are so because we can squeeze more transistors, so then they all have certain functionality, and the additional functionality contributes to the complexity. So therefore, the complexity is increasing. Also, something which was not considered a couple of years ago is that the annual design starts in advanced nodes. So advanced nodes are less than 10 nanometers, are also increasing. So a couple of years ago, there was a discussion. So who will be able to afford all these designs? So because it's very expensive, only very few types of chips it's worth to design them in these technologies. So like CPU or GPU. So only very few companies will be able to do the designs. But now we just see that the demand for advanced nodes chips is much larger than predicted. So it's not only the usual suspects like Intel, AMD, NVIDIA, they are buying our software for design, but also system companies. They are now getting into chip design, and they are designing chips for their specific demand, and they need advanced nodes for this. So we see that the market is for these solutions is growing. But now we have an issue that we don't have enough engineers who are able to deal with this complexity. And in the future, the situation will get even worse. So basically, every professor who here in the room will confirm that the number of students is declining. So who choose to study microelectronics. So this is now considered as one of the top risk factors. And the question is, so how do we solve this? So can we attract more students to study microelectronics, or do we have another solution to this problem? Yeah, so what is the power of humans? So here I'll go back now to the question about the human IQ versus the artificial IQ. So human is good at intuition, judgment, and experience. So a human can do things like algorithm design, innovation of completely new architectures, and think outside the box. And this is also the reason why companies like Cadence, but also in general technical companies, they are running diversity campaigns, because it's proven that a diverse team can think outside the box and find unusual solution because of the mix of different people with different backgrounds. So what is the power of AI algorithms? So the limitation of human is that human brain can do serial data processing. So we are very bad at parallel thinking. And at the same time, this is the strength of AI. So AI can process a lot big data. They can do it in parallel. So it can process the data, it can classify the data, it can generate data. And so most common applications for AI are now chatbots, speech from text, image from text, recommending ads. So now the question is, so how this can be leveraged for EDA? Yeah, so what are we doing during the chip design? So first we create a model, so on a quite a high abstraction level, and then we always analyze, optimize, and refine this model towards till we get at the GDS level, and all the time we must ensure that the model is corresponding to the spec what the final design is supposed to do. And this task is currently done by engineers, but actually this is a task which is quite suitable for AI. So if you use reinforcement learning, so once you create a model, so then you can use reinforcement to optimize the model, to get always feedback if the model gets better or gets worse, and then using the reward function, you can you can drive the optimization towards a better model. So this idea of using reinforcement learning, it's a basis for some tools which I will introduce in this presentation, so that a model gets refined towards better results. So this is a slide which our CEO is presenting quite often, not only to a technical audience, but also to our investors, because so AI is now quite a hot topic. So what's the promise? The promise of introducing AI into EDA. So here we expect 10 times greater productivity. So just to put it into perspective, so 10 times greater productivity we had when we switched from manual circuit design, so with pen and on pen and paper, to automated transistor level design. So when we started to use SPICE, then the next level was the automated cell-based design. So basically the introduction of standard cells, introduction of RTL. And then the next 10-time productivity increase was when we started to use IP. So you can imagine how transformative these processes were for chip design. So from pen and paper to IP, and the same level of transformation is now expected by introducing AI into EDA. So here it's said that this level will be reached by 2030, but already now we see very promising results, which I will also show today. Yeah, so as often in life, so the best outcome you get if you combine both strengths. And so the idea is now to create AI-driven EDA, and this the promise is to accelerate the human in the loop. So the idea is explicitly not to replace the human in the loop, but to keep the human, but accelerate the work of the human engineer. And so now the question is how to achieve that. So the traditional EDA, you basically have different tools for different tasks, so they are integrated into a design flow. But what you basically are doing, so you are always running these tools, then you collect the results, you evaluate these results, and then you just rerun these tools again till you reach the final results. So the final results are meeting PPA goals, meet coverage goals. So basically refine the model till it's complies with the spec. And all the data which are created during the run, so now it's the task of engineer to find the right data out of all the log files, of the result files, and then think so which data are important, which data can be used in order to generate new set of parameters to rerun the tools again. So the idea would be now to take a big data platform and collect all the data which are generated by the tools, and then use AI-driven algorithms to evaluate this data. So to learn from this data, and then based on this data, create automatically new parameters for the tools, and then in order to when the next run is started, so that all the knowledge from the previous runs is collected and applied to this new run of the tools. And then so the expectation is that this way PPA coverage are achieved and improved compared to if a human engineer would collect and evaluate all this data. And of course, I wouldn't present this without a Cadence solution to this, and we call this JEDI. So it seems that at R&D there are some Star Wars fans, and so JEDI is based on Apache Spark. So Apache Spark, this is a solution for so-called data lakes. so where you have a huge amount of data, and then this attaches. So JEDI offers interfaces in Python or in C++. So it's even possible to write own apps which are accessing this data, and then does some operations on this data. And then so we have also tools which are accessing JEDI. So these tools are Cadence Cerebras. So here we had a workshop on Sunday on this technology. So it's for digital implementation. Then we have Virisium for verification. So about Virisium, I will talk a bit later. Virtuoso Studio for custom design, Allegro for PCB design, and Optimality for multiphysics. So I will not touch Virtuoso, Allegro, and Optimality today, but will concentrate on Virisium. Yeah, and so these are not just tools, but these are complete platforms which collect the data. And then based on the data which are saved in JEDI, try to optimize the design flows in order to get better results. And of course, so in the future, it can be expected that more tools will access JEDI and benefit from the data which are saved there. So of course, when we have a technical solution, it doesn't mean that we have a legal solution, because there are all kinds of questions. So for example, if a third-party data can be stored in JEDI. So if, for example, our competition is fine with this, that their data is stored there, or if the user can add some own data. So this is a question. These are questions which will be resolved not necessarily by the technical people, but more by our legal people. So so this slide basically shows that there's a difference between AI-driven platforms. So as were shown in the previous slide, so which are relying on JEDI, and we have also AI-driven tools. And the difference is, so we call this ML inside and ML outside. So ML inside basically means that there are algorithms built in our software which are using ML, but this is completely transparent to the user. So the user doesn't even need to know that there's an ML driven algorithm, and so it's basically yet another algorithm which accelerates the software, so not visible to the user. While AI-driven platform, so here it's clear to the user that here some AI is applied, because this is not only one tool, but it's a combination of tool, and the AI is optimizing. So how the tools are working together optimizes the design flow. So for the AI-driven platforms, so the ML outside, so here I already mentioned these tools, but AI-driven tools, so ML inside. So here we have also a broad palette of tools which are benefiting from the ML algorithms which are built inside the tools and are not visible to the user. So now let's look at one verification solution which is using AI, and this is an ML outside. This is called Cadence Virisium. So in order to understand why this, so we call it apps. So this auto triage, semantic diff, pin down, wave minor debug. So these are apps which are accessing JEDI, and so why are they very helpful? So let me first describe the scenario, what happens in when you develop a very complex SoC, so let's say 7 to 5 nanometers. So usually there are tens or even hundreds of designers who are contributing Verilog. So then there are hundreds of IPs from third party which are integrated into SoC, and so all these designers, they are writing the Verilog code, they are submitting this through GitHub or Perforce, and then at the end of the day, a regression run kicks in, and then so on the other morning, the results of the regression runs come in, and then several tests are failing. So now the question is, so why are they failing? And so which commit was responsible for the errors? So there are, let's say, 100 commits. So how to find out in which commit the bugs were introduced? So here, therefore, so first there's an app called auto triage. So what happens is that the app tries to group the failing tests and assign them to a certain bug. So because if there's a bug in the code, so then it's not one test which is failing, but several tests are failing. And now the question is, so how to find which tests are failing due to one specific bug. And auto triage tries to collect the tests, put them in certain groups, and so here we achieve an accuracy of around 95%, and the user also can manually assign some tests to these groups and train the model. So here the model gets improved with manual input from the user. So once the groups were created, so then we have a semantic diff. So semantic diff basically tries to find out which parts of the code most likely contributed to the bugs. So which parts of the code of all the commits were critical and could cause the errors. Then we have the pin down. So again, imagine you have 100 commits, and one of these commits introduce the errors. So usually what you do, so you do the commits, you rerun the regressions until you find a clean code base, and then you go from there, and then you try to find out which commit, which successing commit was responsible for the error. So pin down automatically finds which commit was the last clean commit, and then you have a clean database, so a clean error-free database, and then you can evaluate what went wrong. So you don't have to rerun regressions. So pin down promises to find the last correct stage. Wave miner, so tries to find out, out of thousands of waveforms, which waveforms do not look right. So which waveforms are most likely causing an error. And then out of these thousands of waveforms, it selects the few ones which are causing errors. And then we have Visuum debug. So if you are familiar with Cadence Indago, so this is basically renamed Indago. So you see that in this scenario with many code inputs, so either from IPs or from designers, to find out where the bug is. So usually around 40% of verification time is spent on finding the bug, and these tools are helping to speed up this process. So here we have some numbers. In September this year, we had a press release about these tools, and so we had partners like MediaTek, Renesas, who provided us numbers, so how their verification was speed up because of using these tools. So these numbers are even better. So they are newer from October this year, and yeah, so you see that that our partners see a significant improvement of their verification time. And so if you look at the numbers, so this is already a kind of a tenfold productivity increase, so which was promised for 2030. So here's an example for ML Insight. So here the idea is, so if you're running a lot of regressions, so usually it takes a lot of time. And so how does a regression work? So you create some tests, and then you try out different inputs to these tests, and you want to have you have such a matrix which we call bins with outputs, and you want that every output, so every bin is covered at least once. So okay, and so this is the way how you achieve coverage, so that all of your output states are tested at least once. So what Cadence Xcelium ML does? It optimizes the regression runs. So at the end, you need less tests, and you need less runs to achieve the same coverage. And sometimes the coverage even improves. So basically, actually at this conference, I learned that there's an expression which is called the green algorithm. And I think this is an example for a green algorithm, because by running less tests with the same result, so you save time, you save energy. So this is how machine learning can help to also to do a sustainable design. Yeah, so we had some examples. So where you see that the CPU cycles are significantly lower compared to the unoptimized regressions, while the regression coverage stays more or less the same. Another example, which I would like to show also for machine learning insight, this is the formal verification. So the problem with formal verification is that there are several algorithms which formally prove that a design is correct, but not every algorithm converges on every design. So therefore, there must be a kind of a match between the design and the algorithm which verifies the design. And so far, it was also a task for an engineer to find the right algorithm. But now the idea was, so first to do supervised learning. So we had like 500 in-house designs, and then we classified these designs. So which design works with which algorithm, and then we already had a solution which improved the user experience and improved the speed of the verification. So of course, after the supervised learning comes the unsupervised learning. And so here, the tool, we call it proof orchestration, basically tries to learn by itself, so which algorithm can be applied to which design. And so we also see that there is a speed up of verification, so that this algorithm is now, so the model is now trained to find this correspondence between design and algorithm. Yeah, and using this proof orchestration, then we have also some other tricks. So how to speed up verification, either by proof caching or by proof profiling data. So we are able to increase the proof success rate and also increase the verification speed. And so this is here how machine learning, so artificial intelligence and human intelligence can work together. So on the horizontal, we have the an application of machine learning. So by finding the right algorithm, verification algorithm through the right design, and on the vertical, we have ways, so how to empower the human engineer, so how to make it easier for the engineer to verify a certain design. So we did it by introduction of verification apps, by profilers, by coverage, and as a synthesis of these two so we have tools like Jasper Expert System, the Verisium apps, and actually today, so later in the day, at Jasper user group meetings, so there will be an announcement of the Jasper Expert System 2.0, so the next stage of formal verification. So if you look out today for the press releases, so you will see this announcement. So now let's come to a bit different topic. So we call our software computational software because it's a very computation extensive. So it uses machine learning algorithms. It runs in the cloud, and so in the past, so like in the 90s, so Cadence has supported several processor architectures. So you might remember Spark with Solaris, or power processors with AAX, or HP processors with HP UX, and we even supported Itanium at some point. But then the combination of x86 with Linux was basically the only platform that Cadence was supporting. But now we see that sometimes it's more efficient to run certain software, so certain tools on a different hardware platform. And this is when we started to support ARM CPU. We started supporting GPUs, FPGAs, and Cadence Silicon, so to run optimized software on this optimal hardware to get faster results and also better results. So let me concentrate on Cadence Silicon and on the FPGA platform. So Cadence Silicon. So here we are designing our own processors and put them into a system called Palladium. And these processors are responsible for emulation of the Verilog code, which needs to be verified. So it's possible by using Palladium solution to trace every bit in the netlist and verify it. So while on FPGA, so as you understand, the if you compile something for FPGA, so then the structure of the netlist gets changed, so it's not as good for debugging. But FPGA can be used in order to start developing of software for a chip which is still in development. So therefore, so Palladium you are using for verification, and Protium you are using for fast bring up of your software once the chip is coming back from manufacturing. And we call this combination of Palladium and Protium the dynamic duo. And it's possible to use the same netlist for both solutions. So there are no manual adaptation is necessary to have the same to have the netlist running on FPGA or on Cadence Silicon. So this is also quite comfortable for the designer. Yeah, and since we understand that not every company can afford to buy the hardware, so therefore we are offering this domain-specific compute in the cloud. So basically, it's possible to access Palladium or Protium or also servers from the cloud. And so we have a Cadence Cloud Service. So that means that we are running this together with our with hyperscalers, so like Azure from Microsoft or AWS from Amazon, and it's possible to install all the Cadence tools in the cloud, to install third-party IP, so that it's a turnkey solution for a designer to start designing. So basically, no CAD team is required who will work on installation, maintenance, optimization of the tools. So this is then done by Cadence. Then we have Cadence Cloud Passport. So this is kind of a hybrid solution, so that the customer can run our tools on his own cloud, so either on his own cloud or on the cloud of a hyperscaler partner of his choice. And now we have also Cadence on cloud. So this is software as a service. So basically, you just buy the software. It's installed in the cloud. So and you can control it via your browser. So you don't need to install it locally, and you don't have to care about the maintenance. So then, just to summarize, so Cadence is offering verification full flow, which is AI driven, and we have different engines. So for formula verification, for functional verification via simulation, for emulation, for prototyping with our FPGA platform, and also for a virtual platform called Helium. So for system C and virtual prototyping. So all these solutions are running on the cloud, and they can store their data in the JedEye platform, so that other tools can benefit from it. So this concludes the Cadence presentation, but I have one more thing to announce. So now I'm changing my hats from Cadence employee to the Young People Program chair at DATE. So since this is an academic conference, so we want that the students are learning about AI. So what are the benefits, what are the risks of it, and therefore I'm announcing the DATE 24 GPT design contest. So the questions to be answered during this contest. So is it possible to increase the productivity of a circuit designer by using GPT? So can GPT produce reliable code from a provided spec? And in general, to spread the knowledge of capabilities and restrictions. So the idea of the design contest is that the partners, which are listed here, are providing a spec, and then the participants of the contest, they use a GPT system of the choice. So it can be an online GPT, it can be a local model, and using GPT, they should create an RTL description of the design, which corresponds to the spec, and then there is a verification step, so which is using verification IP, and then it can be checked immediately if the design corresponds to the spec. So the partners here are ARM, Cadence, TU Munich, University of Southampton, University of New South Wales in Sydney, and Europractice. So the contest will find place on March 24th in Valencia, Spain, so where the date is also finding place, and the students, so the participants, they have 24 hours to create a design. So they can use GPT, they can use also manual editing of the code, also use of Copilot is allowed, but the manual edits, so they must be reasonable, and they also must be marked, so that these are the parts which were edited manually. So 4 persons per team, companies, student group, researchers, they can all participate. And then 24 hours later, on March 25th, there will be the presentation of the results and the award ceremony. So how are the judging criteria? So first, the jury should get access to the GPT system and the model which was used to generate the results. All the prompts should be provided, so for evaluation, and of course the RTL code. And the criteria are that first, the code can be simulated at all, that it is complying with the verification IP, so that's logically correct. Then if you are using an own trained model, so this is valued higher than if you use some standard model like ChatGPT. And so the amount of manually changed code should be reasonable. And then also there will be an interview with the group, and based on the interview, based on the RTL code, so then the winner will be identified. So the prizes, this will be so one prize is a professional program from Stanford, so on machine learning. But if you think that this is not valuable for you, so you can also find a comparable education course, and so the prize will be sponsoring of attending this course. Of course, there will be online trainings which will prepare the participants to participate in this contest. So it's not only about competing, but also about learning of these technologies. So ARM will provide a training on EMBA design IP. So because so what I can disclose already now, so the spec will be about EMBA bus design. Cadence will provide a training on verification IP, and universities will provide a training on GPT. And so here are some FAQs. So the expectation is that at least one member of the group is capable of writing Verilog, while the other members, they can come from computer science. And they have all traveled to Valencia. So it's not an online contest. It's you must be on site. But at least the registration fee for the date will be covered, so that that means that you can also enjoy the date conference. Yeah, so as I already said, online and local GPT systems can be used. And if you have more questions to this contest, so here's the email address. So it's YPP, so Young People Program -industry@dateconference.com. So I thank you for your attention.